As we'll see in later videos, there are several slightly different versions of a basic artificial neuron, but for the purposes of our explanations, we'll stick with one very simple model. A diagram of the basic neuron is shown on the screen, and it has 4 components. Let's go through these one by one. Firstly, we have the inputs, and like the biological neuron, the inputs in the artificial system can come from either the outside world or from other neurons. The inputs are usually numbers restricted between 0 and 1. The second item is the weights. The weights in the artificial neuron represent the synaptic strengths in the biological one. You might remember that synapses can become stronger or weaker, and this is one of the main ways in which a biological neuron learns. In the artificial one, the weight is an unbounded number which multiplies the input, and this makes it more or less important compared with the other inputs. It is the weights which the learning or training algorithm changes in order to make the network learn. Thirdly, we have the summing function. The summing function takes all the weighted inputs and adds them together. For example, in the neuron shown in the diagram, S, the summing function, is equal to input 1 times weight 1 plus input 2 times weight 2 plus input 3 times weight 3, which we could conveniently write in shorthand as S is equal to the sum from 1 to n of Ni Wi, where n is the number of inputs and I is an index. If we consider the inputs as a vector I and the weights as a vector W, we can also write this down as S equals vector I times vector W. Finally, we have the output function. The summing function mentioned in the previous section tells us how stimulated the neuron is. That is, what its activity is. The final stage is to decide whether the neuron fires, that is, whether it sends out a pulse or not. If there's enough activity, we want the neuron to fire, and if not, we want it to stay silent. This was originally done using a threshold function. If the sum is greater than this threshold, then the neuron produces a binary 1 output, and if it is less than the threshold, then it produced a binary 0, or in some models of neuron, a -1. We can conveniently write this as an algorithm. If S is greater than the threshold, then output equals 1. If S is less than the threshold, then output equals 0. The threshold of these threshold units was changed by the training algorithm along with the weights. Another benefit of this is that all the neuron outputs were fixed at either 0 or 1, which made the data easier to handle and to interpret, and made sure that the weights didn't get either too big or too small. Because it squashes the output to between 0 and 1, the output function is sometimes also called the squashing function, and it's also called occasionally an activation function as well. However, the binary outputs of these threshold neurons didn't capture all the information present in the biological neuron. You might remember that in the biological neuron, the pulse frequency could vary anywhere from very high to very low. So a more flexible approach was adopted, one which would allow a low activation to be close to 0 and a high activation to be close to 1, but also allowed values in between, for example 0.5, to express an activation which was neither very high nor very low. The most common of these activation functions is the sigmoid function, which is shown on the screen, where the output of a neuron is equal to 1 over 1 plus the exponential of the minus sum. Sometimes designers of systems chose to squash their outputs between +1 and -1. This is not quite as common but does occur. And in this case, a tangential hyperbolic squashing function can be used where the output is tanh of the sum of a neuron. A summary of the equations for the neuron is shown on the screen. And you might remember from the last video that these simple types of neurons, which are based on the McCulloch-Pitts models, are also often referred to as perceptrons.